Hello everyone, in this video we will be discussing about photoelectric effect. It's a part of class 11 chapter atomic structure. First we will see what is the apparatus which can explain photoelectric effect. So in that what was taken is a tube. A tube was taken and in this tube there were two metal surfaces. One metal surface here and the another metal surface here. So two metal surfaces were taken and then they were connected to, here there was actually a bulb just to show that this is working or not. There was a bulb and then this side, this was a negative plate and this side was a positive plate. And this is again connected to the other metal surface. This is negative we said, this is positive we are saying, and this is the metal surface. This is one metal surface. The other side also, suppose you take a metal surface, this side also suppose you have taken a metal. This side we have taken a bulb. Actually if you just take some metal and light falls on it, electrons are ejected or not ejected, we will not be able to judge it. So as to actually prove experimentally that when the light falls on the surface of the metal, electrons are ejected, this setup was done. And photoelectric effect was explained clearly by Einstein. Using the Planck's quantum theory, that is E is h nu. So what happens is, this metal surface is connected to the negative part of the battery, this one. So this is acting as a negative plate, this is acting as a positive, it is connected to the positive terminal of the battery. And now suppose a light is falling on this plate, light of some frequency nu. Light of some frequency nu is say falling on the surface of this metal, it is falling here. So when this is falling on the surface of the metal, the electrons which are here, this metal is made up of a number of atoms on which there will be electrons, and obviously the electrons which are on the surface, not the ones which are in the core. So core electrons will not participate, only the surface electrons. So when the light of certain frequency nu falls on the surface of the metal, the electrons are ejected. Suppose you do not have this light and just two metal surfaces were there and then you connected and the bulb will not glow because there is gap between. Now if we fill this gap with something, now what are we filling with? Suppose the light is falling on the surface of this metal, electrons are ejected, so electrons will start moving from here. Electrons will start moving. Where will they move? Toward this side, because this is a positive surface of the metal. This is the positive terminal because it is connected to the positive terminal of the battery. So electrons are ejected from here and these electrons start moving toward the positive plate. These electrons are ejected when the light falls on it. So the electrons are termed as photoelectrons. These are called as photoelectrons and the phenomena is called as photoelectric effect. Okay. I think this part is clear, like what photoelectric effect is. Now this this gap is occupied by the electrons, so there is now connectivity. So when electrons are flowing, they will be flowing now in the circuit and the bulb will start glowing. Because the electrons started emitting from this surface, they are going towards the other side and passing through the wire, so the bulb will start glowing. So this is photoelectric effect, right? Now this is basic idea I've given you, like how it works. Now suppose in the same setup I am taking the other way around. Suppose what I do is the light is falling this side. Suppose the light is falling on the positive plate. If the light is falling on the positive plate, will the photoelectrons be ejected? Will the bulb start glowing? Think over it. It will not flow. Reason? Because this is falling on the metal no doubt electrons will be ejected from here. Electrons will come out because light of some frequency nu is falling on it. So electrons will be ejected. But electrons will not be able to travel this side because this is a negative plate. In fact, they will be attracted toward the positive only. They will remain here only. They will not be able to fill in this gap, and the electrons will not be moving in this direction. So in that case, there will be no photoelectric effect. So photoelectric effect will be visible only when the electrons are falling on the negative plate, and then the electrons will be ejected, and these electrons will be moving towards the other side, and we can see that the bulb starts glowing. Okay, so suppose we have to define the photoelectric effect. How are we going to define? We will say when radiations with frequency greater than nu naught. And what is that nu naught? I'll tell you. If it is greater than nu naught means the energy with which this electron is attracted towards the nucleus, because this electron is not just free to move. Of course, when light falls on it, it starts moving. But otherwise, the electron is attracted towards the nucleus. Suppose this was the structure of the atom, and the electrons here, which were present, the valence electrons, they are held towards the nucleus with some energy. That is called as the binding energy. So that means when the light falls on the surface, they have to overcome this binding energy. So if the frequency of the light which is falling on the surface is greater than nu naught. Now what is this nu naught? Nu naught is referred to as threshold frequency. Threshold frequency. So when the radiation with the frequency nu greater than nu naught strike the surface of metal, electrons are ejected. This phenomena is called photoelectric effect. This is called photoelectric effect. And I also specified that the electrons are called as the photoelectrons. Got it? Now one very important thing to understand is that nu naught should be lesser. Or you can, in other words, you can say the frequency of the light falling on the surface should be greater than the frequency or which is contributing ultimately to the binding energy. So what we can say, binding energy is what? H nu naught. Okay, because H is constant. Even here when the light of frequency nu is falling on it, we can say H nu naught will be the energy of the light. Similarly, H nu is the energy of the light, and H nu naught is the binding energy. So that H nu should be greater than H nu naught in a way we are saying. Because H was constant, so we ultimately said nu should be greater than nu naught. Only then the photoelectric effect will be visible. Okay, so just understand this properly, that when the light is falling, energy is H nu. Nu was the frequency of the light. H nu becomes the energy of the light. Energy of light, or we can say energy of the photon which is falling on it, falling on the surface of the metal. That is utilized in two ways. One is to overcome this H nu naught. H nu naught means the binding energy. This is the binding energy. That means it should be able to remove electron from the effect of the nucleus. Binding energy we are saying. Or this binding energy is also referred to as a work function. It is also referred to as work function. Work function. Plus, it is also providing kinetic energy to the electron. So, plus we say kinetic energy. So, this is the final formula for the photoelectric effect. H nu is equal to H nu naught plus kinetic energy. This work function you will also find in different books. The symbol given is either you write down W naught, or at times they also write it as phi. So depending upon that, you can have different ways of this formula writing. So h nu is equal to, you can say phi plus kinetic energy, or you can also write it as h nu is equal to w naught plus kinetic energy. Now suppose we want to find out what will be this work function value for the different elements. Suppose I say some in the periodic table. In the periodic table, the work function will be the least for which elements? Normally you will say the ones which are larger in size, because if the size is large, then the distance between the nucleus and the valence electron will be more. So electrons will be able to come out of the hold of the nucleus easily. So what we can say, suppose you have different metal atoms, say cesium, you have potassium, you have this one, say sodium, you have say lithium or silver or copper. Okay, suppose you write down their 5 values, that is the work function values. If they are known to us, say this is 2.4 electron volt, and this is 2.14, sorry, cesium is 2.14 and this is 2.25, and then comes sodium is 2.30 electron volt, lithium is 2.42, this is 4.3, and this is 4.8 electron volt. These are the different work function values known for different metals. So out of these, which one will be the best metal which can be used as a photoelectric in photoelectric cells? The one that is having the least phi value, the least phi work function value is for cesium, because it is largest in size. The distance between nucleus and the valence shell is maximum, so electrons are loosely bound, they can be removed easily. So cesium is quite commonly used in photoelectric cells. It is used in photoelectric cells. Okay, so we can further modify this formula. We can write, instead of kinetic energy, h nu is equal to h nu naught plus half mv square. We can even write this formula. At times the wavelength of the light is given instead of the frequency. The light which is falling, the photon falling on the surface of the metal, they give wavelength. So instead of this frequency, we can write down wavelength also. Hc by lambda is equal to h nu naught, or we can write again this work function. Depending upon our requirement, we will be using the formula for the photoelectric effect. Got it? So what you can do is, you can draw two important conclusions. That one is nu should be greater than nu naught. Then the photoelectric effect will be visible, right? If nu is lesser than nu naught, the photoelectric effect will not be visible. Even if it is equal to, then kinetic energy will not be there. No velocity will be given to the electron. Or in a other way, we can say that h nu minus h nu naught is equal to kinetic energy. So this is the first conclusion we are drawing, that greater the frequency of the incident light, greater the frequency of the incident light, greater the frequency of the incident light, greater is the kinetic energy. Greater will be the kinetic energy. This is the one conclusion you draw. The second one is increasing intensity of light of given frequency increases the number of photons. It increases number of photons, but does not increase energy. Does not increase energy of the photon. That means by increasing the intensity, the number of the electrons ejected per second I mean, how many electrons will be given out in given time, that will be increased, but not the energy. Okay, so intensity will not be affecting the energy. If we have to increase the energy, that means we will have to increase the frequency of the light, not the intensity. Now let's do one or two numericals based on photoelectric effect. The question says calculate kinetic energy of the electron ejected when the light of frequency this falls on the surface of metal and the threshold frequency is given. That means we are asked to calculate this, this formula we are using, H nu minus H nu naught is equal to kinetic energy. H we can take common, frequency nu and nu naught both are given. So we will write H common, nu minus nu naught is equal to the kinetic energy. Right, so H value we can substitute 6.626 10 to the power minus 34 joules second. Nu is 5.2 into 10 to the power 14 minus 5 into 10 to the power 14, right, is equal to the kinetic energy. So we can just take this common, 10 to the power 14 common, and this difference is 0.2. So 0.2 into 10 to the power 14, this is the the other part, and 6.62 you can multiply with this and get the value for the kinetic energy. So okay, when you solve it, it comes out to be 1.325 into 10 to the power minus 20 joules. Got it? So this will be your answer for the kinetic energy. Okay, let's move on to the next question. It says the wavelength of the light falling on it is given on the surface of cesium. Wavelength instead of frequency, now wavelength is given. Okay, and they are giving calculate the energy of the photoelectron when the critical wavelength or threshold wavelength for cesium is given. So instead of that frequency thing, now wavelength was given. So it's basically Hc by lambda is equal to Hc by lambda naught plus kinetic energy. I think you can try this out on your own, right? So you can bring it on the left hand side. You can take that Hc part common, bring it on the left hand side, and this is 1 by lambda minus 1 by lambda naught is equal to your kinetic energy. And you can just substitute the things because the wavelength is given to you. Wavelength, only thing is you have to convert this wavelength into meter. Okay, so you can substitute all these values and get the kinetic energy. You can pause it and calculate on your own. Okay, the answer comes out to be, just verify the answer, minus 19 joule. This is the answer for the energy given. Okay, I hope you have followed the photoelectric effect concept properly. Practice it well. Thank you.